For this tutorial, I'm going to talk about the following 5 things. First of all, how to show two sets have the same cardinality. Then we'll move on to finite, countable, and uncountable. Then we'll talk about the elegant proof, Cantor's diagonal argument. Then we'll talk about power sets, and then how to show sets are countable or uncountable. First of all, definition. We know that if we have two sets A and B, they have the same cardinality if there is a bijection between them. This means that if you want to show A and B have the same cardinality, you need to come up with a bijective function f that map either from A to B or B to A. Okay, it doesn't really matter which one's which. But if they ask you how to show two sets have the same cardinality, that's what you need to do. Come up with a bijection. So here's one example. I want you to prove the following pairs of sets have the same cardinality. The first one is the interval 0 to infinity and the interval 0 to 1. I'll give you some time to think about it and then we'll take it up. Okay, if you're done with the question, show me your favorite emoji so that I know I can take it up. Good? We're good? Okay. So let's just do this. So I have f that map from 0 to infinity to 0 to 1, and I need a bijective function. Anyone want to share us your function? Anyone want to share us your function? Yes, no, no one, no one share. Okay, so I'll show you one of the function, and actually have multiple functions in mind right now. One of them is this one, arctan x. Okay, so this is one of the function I have in mind. Anyone want to share their function? In case you are wondering, this function would look like something like this, where this is 1, 0. Okay, so not include this point. Another function that I have in mind is this one. Equals to x over x plus 1. Okay, so this function would look like something like this, where this is 1 as well, so not include 0. Okay, I think both of them works. Oh, Jason is just another TA. He was TAing 102 last semester, so he joined this section as a guest. That's why he doesn't need to have last name. Okay, any question?
Yeah.
Yes, okay.
Is coming up with the function the only way to prove the same cardinality?
So what I was gonna mention is that this. So if you used this one, okay, let's say you used this one, I think it's quite obvious that it's a bijection. So you don't. So if you come up with an easy function, let's say not this one, let's say a linear function, then you don't really need to prove that it's bijection. Although the proof is really easy. But if what you come up with is a much complicated function, such as this one, okay, if you have this function, then I suggest you to prove that it's a bijection. Did I answer your question? Yeah.
It's only if it's
So
obvious.
it's, yeah, if it's like really obviously a bijection, then you don't have to show. But if it's not, then it will be better that you show it. To come up with a function that works when working with two sets? Not really, but what I suggest you to do is you need to know it's better that you know as many graphs of function as possible. So for example, some functions you really need to know e to the power of x, ln x, like those functions. Also like arctan, think it looks like something like this. Okay, so and so a lot of other functions. So it will be better that you know the graph of those functions, so that if you, for example, you have a question like this, you know that you need its map from 0 to infinity to 0, 1, so you know that, well, we need some function that look like this, right? Like this part of this function. So that's a bad thing I think you can have. So if you want to be prepared, know as many graphs as you can. Then when you see such functions, you have some kind of intuition. Yes, you can make a piecewise function. Yeah, that's totally fine. If it works, yes. If it's defined and if it works. A lot of the time, the piecewise function you guys come up is not really defined, but just make sure you fix that problem. But if it works, then it's totally fine. Okay, next. Yes, you have a question?
Yeah.
Yeah, okay.
Yeah. For a piecewise function, isn't that like a hack? Because like you can do anything.
Not like you can do anything. It's really helpful. As we said, as long as it works, then we don't really care what kind of function you're using.
Okay.
Okay, let's move on to this question. Again, show me your emoji if you are done, then we can take it up. I'm actually hungry. What did you guys eat for lunch or dinner? Go eat. Are you gonna take over my tutorial, Jason? If I go eat? You ate plain bread for 2 days? Wow. Eat something more, like rice and potatoes and veggies. Okay, nice. I don't believe you. Dumplings. I think I'm gonna eat dumplings tonight as well. I almost forgot I made dumplings before. Okay, anyone done this question? Can I take it up? Okay, what's the answer? So yes, so we can take it up. So one thing that a lot of students make mistakes is that what they think S is wrong. So the set S, what they think it is, it's not the actual S we're talking about here. So I want to write S as like the list of its elements. So can someone tell me what are the elements of S? You can just unmute yourself, as I mentioned. All integers except 0. No.
Like 1, root 2, root
1.
3.
Okay, you're forgetting something. Remember, x is all the real numbers.
Right.
You're missing something, okay? You said 1, okay? I wrote 1, let's write root 2. But can -1 work as well?
Yes.
Okay, so you're missing -1. What's the next one?
Minus root 2.
Minus root 2. Next?
And then root 3 and minus root 3.
Exactly, okay? Oops. So this is my set S. Plus minus of all roots of integers except 0. Exactly, okay? So I think as long as you figure out what your S is, this question becomes simple. But last year, by the way, this is one of the quiz questions last year. But last year, a lot of students, they think our S is like 1, 2, 3, 4, 5, 6, which is not true. Okay, so I think the key thing of this question is figure out what your S is. Then, okay, you might want to mute yourself now because we can hear everything.
Oh, okay.
Okay. So what I'm gonna do is I'm gonna write two different proofs. One is quite formal, the other one is not so formal. I don't know if they allow you to use the drawing arrow thing. That's why I'm gonna show you both. But I personally prefer the drawing arrow thing because I think it's more clear and rigorous. Anyway, so we have f mapped from natural number to set S. And we have natural numbers is like 1, 2, 3, 4, 5, dot, dot, dot. So defined by like this. So we map 1 to 1, 2 to -1, 3 to square root of 2, 4 to negative square root of 2, 5 to square root of 3, and so on. Okay? I personally really like this, but I think they allow you to use this for the past few years, but last semester when Mike was coordinating the course, he did not allow the students to use this because he said it's not formal. So just in case they are doing the same thing this semester, I'll show you an explicit function. So it's still f is still mapped from natural to S. My f of x is going to be square root of x over 2 when x is even, and negative x plus 1 over 2 when x is odd. Okay? Again, I personally prefer this because for two reasons. First, it's really clear that you map what element to what. Second, it's so clear that you don't even need to show that it's bijective because it's clearly bijective. But for this one, it's not so easy to see that it's a bijective function, so you actually need to prove it. Do you know if Marina is fine with it? I think she should be fine with it. But I suggest you guys to ask on Piazza and let us know. Let us all know, just in case. Yeah, just ask them, just in case. I do think this is much better than this, but let's just be safe. Okay, someone ask a question?
Yeah, can you map it from S to the naturals?
Yes. Since we want a bijective function, it doesn't really matter which one you map to.
Can it get easier based on which direction we do it?
Yes, sometimes it's much easier to do one direction than the other, but in this case, I think it's kind of the same. Will the slides be uploaded? First of all, I'm recording this tutorial, so you can see the recordings later. The slides, I will upload them after my Wednesday tutorial. Okay? Any other question? If not, let's move on to the next question. Are we good? Okay, yes, okay. Third question. So we have two sets. A is union of two intervals, B is union of two intervals, and I want you to show that they have the same cardinality. Again, I'll give you some time to work on this and we'll take it up.
I have a question.
Yes?
Can we separate it so we're mapping the interval 1 to 2, 2 to 3, and 5 to 8 to 3 to 5?
Yes.
That make it
So
easier?
you're thinking about a piecewise function.
Yeah.
Yeah, that's exactly what you need to do. Well, what's going on in your house? Why do we hear that sound? What is that sound actually?
That's my chair.
Oh, okay. Well.
I need WD-40.
You need a new chair.
Yeah.
Yeah,
IKEA has a good one.
buy a new chair as well.
Chairs are actually surprisingly expensive.
How much is it?
I picked this up out of someone threw it out, so I just took this chair.
It's a good deal.
100% discount.
I guess that's why it's not good. Anyway, again, show me your favorite emoji once you're done with the question. You're good? You finished your question? You can't reach the table. Just do everything on your bed. I was gonna run my tutorial on my bed. But I might fall asleep, so I'm like, okay, never mind. Onwards. Okay, let's take it up then. So as someone mentioned before, we can use a piecewise function for this one. So before that, let's draw a graph. So 1, 2, 3, 4, 5, 6, 7, 8. So 1 to 2, 5 to 8. So this is my A, and 3 to 5. This is my B. Okay, actually I changed the question so that it's much easier. Anyway, so what we want to do is we want to find a function that maps from A to B. Basically, you want to do something to A so that it looks like B. So we want to do something to A so that it looks like B. So like this. Okay? So again, someone mentioned that we need a piecewise function, so I'm gonna write that down. Let's say a to b, f of x equals to something, as one of you mentioned, we want to map 1, 2, 2, 2, 3, and then map 5, 8 to 3, 5. Okay, so when x is in 1, 2, you want to map this to 2, 3. What can you do? What is a function that can map 1, 2 to 2, 3?
Just like x plus 1.
Exactly, okay? Just x plus 1. So if you look at the graph here, okay, so basically we just shift this to the right by 1 unit. 1, 2, shift to 2, 3. So that's exactly what we need to do, okay? What about the other half? When x is 5, 8. Anyone has any idea? How do we map from 5, 8 to 3, 5? So basically, I want you to map this to this. First of all, we notice that this part has length of 4 units, but this part has length of, wait, did I change something? Yeah, okay. This part has a length of 2 units, so I changed the question to even easier. Anyway, now what we want to do is, because we want to map this to that, so we want to shrink it to 2 units. What can we do about that?
Isn't it 3 units for 5 to 8?
5 to, oh, it's 3 units. Sorry, yeah, 3 units. So how do we shrink 3 units to 2 units?
3 over 2x?
3, no, you're almost there.
2 over 3x.
Exactly, 2 over 3x. Okay, that's our first step. So after this, what do you get? So 5, 8. After you multiply 2 over 3, what do you get? Anyone want to share? Anyone? So you multiply by 2 over 3, what do you get? 5
With
or 10?
what? Oh, you get 3.38.
Let's use rational, please.
10 over 3.
What about the other?
16 over 3.
Okay, exactly. Now we have this, but we want to map this to 5, 8. What can we do?
Divide by 2. No.
You want to shift this to 5, 8.
Can we subtract by 1/3?
Exactly. Okay, minus 1/3. That's it. So this is your function. Okay, any question?
If you put 5
No, it's not
and
5,
8,
it's 3, 5. It's 3, 5, sorry. It was 5, 8 your origin, and you map to 3, 5.
oh right,
I wrote it wrong.
if you put 3, 5 in the common denominator as 10 over 3, then is it easier to see the relation?
Yeah, I wrote it wrong. Yeah, it should be 3, 5. So
Okay.
we want to map from 5, 8 to 3, 5, and that's what we did here. Here you minus 1 over 3. Any question? Nothing?
No.
Nope. Okay. Continue. So right now we want to talk about finite countable and uncountable. First of all, one of the theorems is that we know the cardinality of natural number and the cardinality of rational numbers are the same. The proof is in your course notes. Also, Professor Ali uploaded a video about it, so you can have a look. The proof itself is really important. We use that proof all the time. Okay, it's like a application of that proof. So please have a look at that. The definition is that if we talk about the definition of countable sets in 102 is that a set that has the same cardinality as natural number are called the countable sets. So if you look at this definition, you should know that, well, you should notice 3 things. One thing is that we know natural numbers is countable. Also, rational numbers are countable as well. Okay, so you know those 2 countable sets. Also, you should know that the finite sets are not countable because it does not have the same cardinality as natural numbers. Okay? Then move on to the next definition. An infinite set that is not countable is called an uncountable set. One of the most famous one we know is the set of real numbers is uncountable. Also, the proof is in the course notes and the video lectures. The proof came up by Cantor, and the technique we use is called Cantor's diagonal argument. It's a really interesting, elegant proof, and here is one of the application. So I want you to use Cantor's diagonal argument to prove that the set of infinite 0-1 sequence is uncountable. Okay, again, I'll give you some time to think about it and we'll take it up. Again, if you are done, show me your favorite emoji so that we can move on.
I don't think anyone understands this theorem because it's too confusing.
So you guys don't understand the theory at all?
No, all I understood was the picture, but like the words made no sense.
You mean you don't understand the theory or the proof? The
The proof.
argument itself. Oh, okay, I see. So, since you guys don't understand, we'll just do it, and I can explain it to you so that you can write your assignment. Okay, I think they want you to prove something really similar on your assignment as well. So what we want to do is we want to use proof by contradiction. Okay, so we suppose this is countable, and then we want to reach like a contradiction later. So I'm gonna write proof for contradiction, suppose, let's call this set A. Suppose A is countable. So by definition of countable set, we know that it has the same cardinality with natural number, which means there exists a bijection between A and the natural number. So I'm just gonna suppose we have a function f that maps from natural number to A, and this function is a bijection. This is my assumption because I suppose that it is countable. So if it's countable and it has the same cardinality with natural number, if it has the same cardinality with natural number, then there exists a bijection between the set A and natural number. So that's what I'm using right now. Any questions so far? Okay, no one said anything. I suppose there's no question. Okay, so since F is a bijection, then we can write A as a set F1, F2, F3, F4, and so on. Okay, we can write A as this because it's a bijection, which means it's surjective. In other words, its image equals to its codomain. This is the image of the function, okay, equals to its codomain, which is A. Now, I'll talk about the logic of this proof. So right now, since we have a bijection, what I want to do is I want to find a contradiction. So I'm gonna find something that's, I want to find a new sequence, okay, a new infinite 0, 1 sequence that is not from the set A. Since we know that A contains all such infinite 0, 1 sequence, so, and it's a bijection, which means like we cannot have any sequence that's not from A. But right now, I want to find a new sequence that's different from all the sequence in this. So in that case, I can show that F is not a bijection because it's not surjective. So that's the logic here. Right now, I'm just going to define a new sequence. Let's call it Z equals to Z1, Z2, Z3, Z4, dot, dot, dot. It's an infinite sequence of zeros and ones defined as below. Defined as follows. So right now I want to define my Z. For any k in natural number, zk equals to 0 if the kth digit of fk is 1. And it is 1 if the kth digit of fk is 0. So what I'm doing here is this. Let's suppose that f1 is a sequence like 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, something like this. F2 is a sequence like 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, something like that. Just make something up. Let's say this. F4 is something like 1, 0, 0, 1, 1, 1, 1, 1, and so on. So my new sequence, what I'm doing is like my new sequence Z looks like this. So first of all, I pick Z1. So Z1 is 1k equals to 1. So I look at the first digit of F1, which is 0 here. Since this is 0, I want it to be different from F1, so I'm gonna pick my first digit as 1. Now if we, what's my Z2? It's gonna be the second digit of F2. So this is 0. I want to pick a different one, so I'm gonna go with 1. The third one, again, I look at the third digit of F3. This is 0, so I don't want it to be the same, so I pick 1. The fourth one, again, 1, 2, 3, 4. The fourth digit of F4, which is 1, I want it to be different, so it has to be 0, and so on. So if I pick in this way, my new sequence here is gonna be different from every single sequence in A. Okay? Yes.
In MAT102, was Cantor's theorem ever on a test or quiz?
It was on one of the quiz.
What did it ask exactly?
I think they used, it was like really similar to the question I gave to you, except they used AB.
Okay, and over here, what's the Z1?
AB sequence. Z1 is 1. So Z1 is the first digit of the sequence.
And it's all the naturals, Z1, Z2, Z3?
No, not all the naturals. Those can only be 0 or 1 because it's a 0-1 sequence.
Oh, okay.
Okay, does that make sense to you now?
Yeah.
Okay. So as you can see, if I construct my sequence Z in this way, then this sequence, now the sequence Z differs from each of the sequence f of k. In other words, f of k does not equal to z for all k in natural number. Yes, question.
I don't. Why do we know that this is going to be a different sequence? I don't.
Oh, here is a reason. It's because how we construct it. Because, okay, if you look at this sequence, okay, if you want to compare this to the first one, F1, we know that the first digit is different, so it's different from the first one. Even if every other sequence is the same, we know that the first digit is different, so it's different from F1. If you compare it to F2, the second digit is going to be different, and so on. So we know that it's definitely going to be different from any of the sequence in A.
Okay, I see
Does that
now.
make sense? Yeah?
Yeah.
How did you write F1, F2, and F3? Like, how do you know what the order is?
It doesn't matter. It doesn't matter. We don't know what they are. So my f, all I know is a function, a bijective function that map from natural to A, but I don't know what my f1, f2, f3 is. So that is why you can ignore the blue part, only look at the red part. This is a part I construct my function. You don't need to show what f1, f2 are because you don't know what they are. I wrote it to give you an example to show you that how we actually construct our sequence. But the red part is the real proof. The blue part is just I gave you an actual example to show you. Okay? Don't know what f1, f2 are. That is why we construct our sequence zk like this. Because if the first digit is 1, then we pick 0. If the first digit is 0, then we pick 1. Because we know that it can either be 0 or 1. It cannot be both. Any other question? So for your question, do we have to show f1, f2, f3 in the proof? You don't. That's not part of the proof. Anyway, I'm just gonna finish writing the proof. Remember, only the red part is real proof, okay? This shows that F is not surjective. Because we found something, okay, we found a sequence, a 0, 1 sequence that cannot be mapped to. Therefore, A is not countable. Okay.
How does this compare to the naturals?
The naturals. It does not compare to the naturals. We just have a function that maps from natural to A.
Right, so where would you
So
find
here, this is your natural. 1, 2, 3, 4. Remember, a natural is your input.
Right.
So as you can see that it's not countable. Okay, I'm just gonna move on to the next one. So if we have to prove that some set is uncountable, do we have to make the naturals the domain of our created function? We'll talk about that later. Actually, I actually have a slide for this. Okay. Next. So I want to talk about power sets. First of all, definition: the power set of a set X, denoted by P of X, is the set of all subsets of X. And Cantor theorem is quite important as well. You need to know that the cardinality of X and its power set do not have the same cardinality. Specifically, if you know that X is finite and it has n elements, then the power set of X has 2 to the power of n elements. This is really important. It tests you many times on the exam, so please make sure you note this. Okay, now let's do questions. So I have set A be 1, 2, 3, and I want you to fill in the blanks with either an element of or a subset.
Can we just go back to the last slide one more time?
Yeah. Do you have a question, or you are trying to copy down something? I'm gonna post the slides anyway.
I'm just trying to copy it down. Is it in the textbook? I'll just look at the textbook then.
The textbook should have it too.
Okay, thank you.
You can also take a screenshot.
Yeah, you
Yeah,
can
you
also
can go to
take
the
a
next slide.
screenshot. Okay, now because we don't have enough time, let's just do it all together. What is the first one? Is it element or subset?
Subset?
Yes, subset. What about the second one? This one, element or subset?
Element?
Okay. Third one?
Subset?
Fourth one?
Element?
Okay, the fifth one?
Element.
Okay, so I have a question for you guys. Before we do this one, I have a question. If I have this, what do I fill in here? Someone said subset. Can we put element here as well? Yes, we can put element here as well. Okay? So we can put element here because it actually is an element of power set of A. We can put subset here because the empty set is subset of any set. So go back to this. What do we put here?
Just element.
Why is an element? We just showed that the empty set is the element of power set of X of A. Now we're talking about the set of empty set.
Yeah.
Okay, it is a subset. Next. A is an element or subset of power set of A.
Element?
Next. Last one, element or subset.
Element? No.
Nope.
Yeah, subset.
Okay, this is because A and the empty set, those are the elements of this. So it's a set that contains the element of the power set of A, which is a subset of power set of A. Okay? Remember we did those two? We did this. We did this. You should know that those two are elements of power set of A. So if you have a set that contains the two elements of power set of A, which should be a subset of power set of A. Does that make sense to you?
Yep.
What's up, Jason? Jason, are you gonna say anything? Okay, let's just ignore him. Let's move on. So, what I listed here are some common countable sets and common uncountable sets. You can take a screenshot, and also I will post the slide later on Wednesday, so you don't have to copy them down. But one thing I want to mention is that although I list them out, it doesn't mean that you can claim them to be countable or uncountable directly. If you want to you still have to prove them because most of them are not proved in your course notes. Also, one thing I want to emphasize is that countable sets have the same cardinality, but if we're talking about uncountable sets, then they might have different cardinality. So it doesn't mean, for uncountable sets, it doesn't mean that they all have the same cardinality with a real number. So that's my point. This one, we don't have time to do it. Okay, so to answer one of your questions, someone asked me how to show a set is uncountable. So first of all, if you want to show a set is countable, then you need to show that it has the same cardinality with a natural number. So this one should be easy for everyone. If a set is uncountable, okay, what you can do, first of all, you need to think about what is a cardinality. If it has the same cardinality with a real number, then you can have a bijection between your set and the real number or the interval 0, 1, because we know that the real numbers and the interval 0, 1 have the same cardinality. What if the cardinality is not the same as the real numbers? Then, well, it might have the same cardinality with a power set of the real numbers. Okay, so you can have your bijection there as well. If none of the above work, well, again, you can use contradiction, suppose it is countable, and then do something, reach to the point that it's not countable. Also, you can do the following. You can show that the cardinality of that set is strictly larger than the cardinality of the natural number. Okay, so here is the definition we can use. We know that A and B have the same cardinality if there is a bijection. If A is if the cardinality of A is less than or equal to the cardinality of B, then if there is an injection, again, same thing for surjection. So what you can do is that you can show that one thing is less than or equal to that, and then you show that they are not equal. Okay, so because this one can only give you less than or equal or greater than equal, you also need to show that it's not equal if you want to use it in this way. I don't think you guys will reach to the point that you to do it because they don't give you hard questions. Anyway, Schroeder bursting theorem. This theorem is amazing, but they never let you to use it, so don't worry about the application and stuff. But the theorem itself is really important. Please know this for your future courses, okay? Again, if you want to know the application, I'm not going to show you because they never let you to use the theorem itself. No, I just want to show you my cat because I like number 19. Oh, this slide is when I just adopted him. That's when he was like, I think 8 weeks, 2 months, around 2 months old. And then you can see he grows really fast. You're 19. You grow older. I just really like the number 19. Okay, this is the last one. If you don't have any question, I'm just gonna move on to my next tutorial.
Okay, bye-bye.
Bye. Yo, Jason, I used 5 because I wanna follow what they did in the course notes, because shy folks use the same thing, and I don't want to change that. Otherwise, if I want to change that, I want to change the name of Schroeder-Burstin theorem as well, because it should be Cantor Schroeder-Burstin theorem, but I want to do it just like what I did in the course notes. What do you mean screw Cantor? I like him. Come on.